Hello everyone. So let us study moment generating function. We can also write moment generating function as MGF. If x is a discrete random variable, moment generating function of the random variable x is denoted by mx of t and is defined as summation of e power txj, probability of x equal to xj if x is discrete and mx of t is integration of e power tx function of x dx if x is continuous, where x varies from minus infinity to plus infinity, and in case of discrete random variable j varies from 1 to infinity. Now in one dimensional random variable we have seen expectation of the random variable x is integration of x into f of x dx, where x varies from minus infinity to infinity when x is a continuous. If you put x equal to e power tx, expectation of e power tx will be integration of e power tx f of x dx, where x varies from minus infinity to infinity. If you see the definition of mx of t when x is continuous and expectation of e power tx, the right hand side of both mx of t and expectation of e power tx is same. So we can say moment generating function of the random variable x is nothing but expectation of e power tx. So I'll take it as equation 1. Now let us differentiate moment generating function of x with respect to t. That is mx dash of t is d by dt of integration of e power tx f of x dx, where x varies from minus infinity to infinity. So f of x, the function of x is treated as a constant since we are differentiating with respect to t. So the differentiation of e power tx with respect to t is x into e power tx f of x dx. So now at t equal to 0, mx dash of 0 will be integration of x into e power 0 is 1. So x into f of x dx from minus infinity to infinity. This is nothing but expectation of x. So expectation of the random variable x is mx dash of 0. That is derivative of moment generating function at a t equal to 0. Similarly, if you differentiate mx dash of t with respect to t, we get mx double dash of t at t equal to 0, mx double dash of t will be mx double dash of 0. We get it as expectation of x square. So on, in general, nth derivative of mx of 0 will be expectation of x power n. So now we have seen mx of t is expectation of e power tx. So I will expand e power tx in terms of power series. So expansion of e power tx is 1 plus tx plus t square x square by 2 factorial, so on, plus t power n x power n by n factorial, so on. So now operate e on all the term, expectation of 1 plus expectation of tx, so on up to expectation of t power n x power n upon n factorial. So now expectation of 1 plus t into expectation of x, since t is a constant, t power n upon n factorial expectation of x power n. So we can see here The coefficient of expectation of x power n is t power n upon n factorial. So we can write expectation of x power n as a coefficient of t power n upon n factorial in the expansion of moment generating function of the random variable x. So this is one of the property of the moment generating function. So we have seen expectation of x is derivative of moment generating function at t equal to 0, and expectation of x power n is coefficient of t power n upon n factorial in the expansion of mx of t. So there is one theorem. Suppose x and y are independent random variables and z equal to x plus y, and let mx of t and my of t be moment generating functions of random variable x and y respectively, then mz of t equals to mx of t into my of t. That is moment generating function of the variable z is product of moment generating function of the variables x and y, random variables x and y. Okay, to prove this, let us consider moment generating function of the random variable z, that is nothing but expectation of e power tz, that is expectation of e power t into, so it is given that z equals to x plus y in the question or in the theorem statement of the theorem. So I'll replace z by x plus y, expectation of e power xt plus ty, so expectation of e power tx into e power ty. So this is nothing but expectation of e power tx into expectation of e power ty. So that is because we have seen a two-dimensional random variable, expectation of x into y is expectation of x into expectation of y if x and y are independent. So that is another theorem. It states that suppose the random variable x has a moment generating function mx and y equals to alpha x plus beta, then moment generating function of a y, that is my, is given by e to the power of beta t into mx of alpha t. So we know my of t equals to expectation of e power ty. Now expectation of e power t into y I'll replace with alpha x plus beta, expectation of e power alpha xt plus t beta. According to the by property of expectation of the random variable, the constant will comes outside, so e to the power of beta t will come outside, expectation of e power alpha xt, so e to the power of beta t into expectation of e power alpha xt by the definition of moment generating function. This is nothing but mx of alpha t. So next we'll see how to find moment generating function of binomial distribution and also expectation and variance of the binomial distribution using moment generating function. So this is one of the application of the moment generating function. Using moment generating function we can find expectation variance of any distribution. To find MGF of binomial distribution, we'll consider probability distribution of the binomial distribution. That is, probability function of binomial distribution is ncx p power x q power n minus x. So next, since the binomial distribution is a discrete probability distribution, we'll use the definition of moment generating function when x is a discrete. That is, mx of t equals to summation of e power tx p of x, that is summation of e power tx p of x is ncx p power x q power n minus x, where x takes the value from 0 to infinity. So I'll expand this, we'll get e power t into 0, that is e power 0, nc is 0, p power 0, q power n minus 0 plus e power t nc 1, p power 1, q power n minus 1, so on. We'll get e power nt ncn, p power n, q power n minus n. So this is nothing but binomial expansion of e power t into p plus q power n. So this is a moment generating function of binomial distribution. So next we have to differentiate this with respect to t. So that is mx dash of t. So the differentiation of this is n into e power t p plus q n minus 1 into e power t into p. Then at t equal to 0, we get mx dash of 0 as, we'll put t equal to 0, that is n into p plus q power n minus 1 into p into e power 0 is 1. Further, p plus q equals to 1 because p is a probability of success and q is a probability of failure. Probability of success plus probability of failure is always 1. So we get n into p. So mx dash of 0 is nothing but expectation of x. So this is a mean of the binomial distribution. Mean of binomial distribution is np, where n is a number of trial and p is a probability of success. Similarly, we'll differentiate it again with respect to t. We'll differentiate mx dash of t with respect to t. So using the product rule, so we can keep n and p outside since it is a constant, and we'll differentiate the product of these two using product formula. So e power t p plus q power n minus 1 as it is, I'll keep. The differentiation of e power t is e power t plus the second term as it is, e power t. I'll differentiate the first term, that is n minus 1 into e power t p plus q power n minus 2 into p into e power t. So next we have to put t equal to 0. Mx double dash of 0 we get as n into n minus 1 into p square plus np. So now this is expectation of x square. Now we know that variance of x is e of x square minus e of x whole square. So e of x square is n into n minus 1 into p square plus np minus e of x whole square, that is n square p square. So simplifying that, we'll get np into 1 minus p, that is n into p into q. So the variance of the binomial distribution using MGF is npq. So this is how we are finding expectation and variance of binomial distribution using moment generating function. So next we'll see how to find MGF of a Poisson distribution. The similar way we have to find MGF of Poisson distribution. We know the probability function of the Poisson distribution is e power minus lambda power x upon x factorial, where x takes a value from 0 to infinity. So since the Poisson distribution is again discrete probability distribution, mx of t is a summation of e power tx into p of x, where p of x is e power minus lambda power x upon x factorial, where x takes the value from 0 to infinity. E power minus lambda is a constant. We'll keep it outside and we'll expand this. E power 0 lambda power 0 upon 0 factorial plus e power t lambda upon 1 factorial plus e power 2t lambda square upon 2 factorial, so on. So this is e power minus lambda into e power lambda into e power t. This is e power lambda into e power t minus 1. Then we can find expectation and variance of the Poisson distribution MGF, just like how we have solved for a binomial distribution. So we have to differentiate mx of t with respect to t once, that is mx dash of t. It will be expectation of x. Then we have to find out expectation of x is mx dash of t at t equal to 0. Then we have to find mx double dash of t at t equal to 0, mx double dash of 0, that will be e of x square. Then variance of x will be e of x square minus e of x whole square.